Hello everyone, my name is Vicente Gonzalez. I'm a staff member at the University of Oakland. So I want to talk about this research, which is part of a large research project we have been developing in New Zealand in the space of quake evacuations. And we work with a number of colleagues across New Zealand and at the University of Canterbury, Opus International consultancy company, but we work with the research department of Opus and Technical Israel. So before I start, I would like to make a sort of disclaimer. I'm going to explain a little bit of the things we presented in the paper, but I want to extend a little bit of discussion in the case study we're developing actually. Well, our former director of the Ministry of Civil Defense and Emergency Management, John Hamilton, said that the aftermath of the earthquake in Wellington in 2013, what we saw was that many people knew, drop, cover, and hold during the quake, but most did not know what to do afterwards. That's the problem, essentially, with our reaction after a quake. We don't really know what to do after a quake. Maybe we are very well trained in terms of what to do during a quake. In New Zealand, the framework and all the infrastructure in terms of preparedness for disaster, because we have a lot of them frequently, it's quite good. However, people, in terms of quakes, don't really know what to do after a quake. And this is the main motivation that sort of pushed the development of this large research project. When we think about what are the recommended behaviors and actions in New Zealand, and this is sort of a reflection also of international research, is during the pre-earthquake stage before the quake, essentially we plan and we prepare people and we train people. And during the quake, essentially it's don't cover alcohol. And what happened after the quake is, among other things, you can see a very long list. I put it on purpose because it's a very long list of expected actions which represent the best practice during earthquake evacuation. For example, keep your belongings after the quake, try to help people, check yourself if you are injured, check potential evacuation routes, etc. And the rationale behind is because during fire evacuation, for example, what you do is essentially run away as long as you know that there is a fire. During a quake, and after a quake essentially, you don't run, you don't rush, you don't leave the building straight away because you are at risk to be hit by debris falling down. And that's the reason, because we have to check, for example, what's going on in the building, wait for instruction from a warden of the floor, for example, etc. So there are many instructions, and it can become a bit confusing for someone to understand what to do first. So this essentially is also another motivation to develop this research. So we identified essentially a few research gaps. First of all, traditional training approaches such as evacuation drills cannot be used in buildings which occupants cannot easily leave the building, for example, hospitals. And also, these traditional approaches may not provide intended learning outcomes and do not allow for an investigation of the impact of multiple evacuation factors on behavior. So one of the things we're going to discuss is about how we can integrate different tools and different approaches, technological approaches, such as virtual reality and serious games, and how we can encourage people to learn specific actions after a quake, improve their preparedness levels, and also how we can provide an environment which is engaging, realistic, that you can believe, okay, this is a quake, I'm going to learn something that's going to be significant for my protective actions during and after a quake. So when you think about developing an earthquake, I skipped the question. So can virtual reality technology help to overcome those limitations? So when we talk about developing a sort of virtual reality environment, we need to think about a number of factors or aspects that can mimic a realistic representation of a quake inside the building. First of all, earthquake features. How we can sort of represent or transfer this sort of feeling of a quake to a person. So we need to think about physical perception using haptic systems. So there are a variety of systems. For example, you can use shaking tables. You can use seats with sort of shaking system that can emulate, the vibration during a quake. You can use gate controllers. In this research, for example, the best compromise that we found was between gate controllers and shaking tables. Just we develop a sort of chair that can help us to make a vibration during our earthquake. The second aspect is the building selection and representation. So what we need to do in order to represent a three-dimensional geometry of a building and the properties of a building. So we need to use an existing building, which implies to collect data of a real building, to develop a three-dimensional representation of that building, and then to export it to an engine, a game engine, in order to develop the virtual reality visualization or simulation. So we can test, for example, how familiar people are or evacuees are in terms of the evacuation plan, or we can, for example, understand, for example, if those people are suitable, understand the evacuation plans, but also are able to sort of implement effectively those evacuation plans during an actual simulation. On the other side, you have hypothetical buildings in which you represent an X building that not necessarily makes sense for an evacuee in terms of familiarity, but provides flexibility in order to develop different sort of scenarios in VR. A third element is damage representation. We can represent the damage given by a quake mathematically or in a qualitative way. So when we're talking about mathematically, where we can use a simulation, considering many aspects of the quake, ground motion, characteristics of the building in terms of physical properties in structural elements, non-structural elements, the reaction or response against a quake. We can use fragility functions to represent the damage on non-structural elements of a building. And when I'm talking about non-structural elements, I'm talking about partitions, elements attached to walls, etc. But the number of assumptions we can make is large enough to develop something realistic that in the end is going to be as good as a sort of qualitative representation. Because what we need is to generate a realistic representation of in a three-dimensional environment. People don't know how much in terms of magnitude the quake was, or what is going to be the real response of the building. There are some reasonable assumptions you can make in order to visualize and generate an experience which is significant in terms of learning, in terms of emotional stress and involvement, but not necessarily we need to develop something that is mathematically accurate. And the fourth element is agent behavior and player-agent interaction. When we started this research, we got an assumption. We need to use agent-based models to represent non-playable characters. Those characters or people moving around when you are playing, a kind of a first-person video, like a first-person video game. And we explored the behavior of individuals during fire evacuation and other disasters other than quakes. And then we realized, well, what we need to understand is human behavior under the effect of a specific hazard, but not necessarily make a simulation of it, because every time you develop a simulation in a sort of in a framework virtual reality series game, what you really need is to represent the same situation over and over again for different people, and just change different parameters according to what you want to achieve. So essentially, we understood those sort of characteristics. For example, we know that people react in a quake in function of their perception to the quake and the movement of the floor. Also, we know that people don't really have this sort of panic behavior during hazard or disaster, because in reality, people make smart decisions. according to the time you have available, according to the available information, and according to the level of stress and fear. Of course, there is a trade-off between all these elements, and in the end, maybe you have a lot of fear, and you're not going to consider that much the information, but in the end, you have to consider and make decisions based on certain cues. So once we understood this, we sort of decide, okay, the research objectives that we need to consider to develop an immersive virtual reality series game are two. First of all, we need to understand behavior using virtual reality and see what people do in a real quake, during and after a quake, with no feedback, no learning outcomes, to observe how much a person can follow regulations or recommendations or guidelines to evacuate a building. And then we implemented a virtual reality series game to train people, defining very specific learning outcomes based on a variety of information. For example, evacuation plans, regulatory regulations about what are the best practices after earthquake evacuation. For example, one of the slides I show you in terms of all the actions you can follow. And we implemented it, in Unity, and we use Oculus, also HTC Vive, to implement the immersive virtual reality series game in the virtual reality experiment. The method to test this was essentially, we combined literature study, computer research and development, understanding of all the elements we need to include to make a realistic simulation in order to understand behavior of people during and after a quake and in order to train them. So we selected Oakland City Hospital because, hospitals are critical infrastructure that should be available during and after disaster. So this was a very interesting case study. Auckland City Hospital is the largest hospital in New Zealand, and we got access to data and information from that hospital. So essentially, we analyzed, and we are analyzing actually, the main building of Auckland City Hospital. We have a large pilot study in a few more weeks. During 3 weeks, we are going to test the virtual reality experiment for behavioral studies and serious game in around 200 or more people. And how we develop essentially the models, we undertake quite a bit of work developing the main models of Auckland City Hospital, and then we imported it through 3ds Max into Unity. And there was a lot of more work that I don't think I have time to talk, but I just want to show you what we developed. First of all, we developed the why I cannot. Give me a second. I think I want to show you. Well, anyway, this is the Auckland City Hospital. Oh, great. Well, this is the sort of visualization, external visualization of the hospital, because when we leave the hospital, you have to have a sort of realistic representation of the whole hospital, but in reality, we model in detail 2 levels of the main building. Then I'm going to show you, if I have some minutes, sorry, I don't know what I'm doing. Oh, great. Well, this is a prototype of the VR experience to study behavioral reactions of people after a quake. This is not the training tool. So we have access to the main entry of the hospital. Essentially, there is a sort of pre-introduction of how to use and control the avatar during the game, during the virtual reality experience. This is not a serious game because we don't provide learning outcomes. So we direct a person to a sort of meeting room. A person is supposed to have a meeting with a GP in a specific meeting room of the hospital. We spend some time before this experience in order to sort of train the person, because we have people with different levels of skills with gaming, different experience with Quake, etc., etc. And then you start the experience. So we start having the experience in itself and observing what, for example, if the person drops cover and fall or not. In this case, well, it's a I did this simulation, so I drop cover and fall to show you that this is what you need to do. We sort of use some elements of protection motivation theory in order to make a very emotional representation of the quake, so people can believe that this is a real quake. Also, you have we sit people on our sort of checking table, in which we put on it on top of that a chair, and people can feel the fear of a quake. And then we essentially observe what are the different actions and intent of people. So people speak aloud about what are the decisions they are planning, they are intending to do. So essentially, this is the simulation. I think I don't have much time, but this is the conclusion. Well, virtual reality serious games have both advantages and limitations for investigating human behavior during earthquake evacuations and for training building occupants to deal with such emergencies. So we have a number of open questions. How real do the physical and social environment need to be, for example, to earthquake? What types of learning algorithms are suitable to set up a credible and practical serious game? What sort of earthquake stages should be considered when crafting the storytelling? Or how can we effectively measure behavioral impacts and learning and research? Thank you very much.